I actually just read an analysis book that actually uses a weird chain for the natural numbers. I don't know if anyone's seen that. But if it comes up, some books use this for some damn reason. I've never seen this before, like yesterday. So, but anyways, the integers, right? This is like all the numbers, both the positive and negative natural numbers and zeros, right? Great. And then of course we have Q, and I'm not going to define these very well with these are the rational numbers. And this is basically all numbers that can be written as P over Q or P and Q are integers. Or I'll say N over M. Okay? And I'm assuming you guys all know this. In fact, yeah, I'm not even going to construct them. So one of the big theorems of the week, I'm probably not going to prove because Rudin takes 2.5 pages to prove it. I may save it for one of those the day before the final kind of lectures or day before the midterm kind of lectures, where it's a really cool idea. It's just, it's a day. It earns a whole day to prove everything about it. But anyways, the point is, these are the ones we're generally aware of. And I know you guys know what the real numbers are. But I'm going to pretend we don't, and I'm going to explain to you what's wrong with Q. So, if you've taken other classes, you might already know Q's not so bad. But let's just find out. So, an analysis is, we're going to be sort of trying to build the calculus. In calculus, a lot of the things we want to, there were limits and all this other stuff. You kind of know where we're going. One of the big issues with Q, and I'm not going to say this precisely right now, but the idea is that it has gaps. It has holes in it, right? If you were to draw what Q looks like, it looks like a number line, but really just a lot of dots. I don't remember that painting. Remember this? I don't remember this. This is impressionist style where you draw everything by doing a lot of little dots. What? Yeah, thank you. Yes, it's like that. But that's if you drew the real line under that style. Whatever. The point is, Q has a ton of gaps all over it, right? And that causes a problem. But let's express it in a specific way. So one way of saying is not all numbers we want are rational. And so I'm going to start by proving this simple thing. Root 2 is not a rational number. And again, this proof, I'm just going to do some simple things just to introduce the style of this class. And then we'll actually start with material. But I just wanted to show you this proof. I mean, this is how Rudin starts too. I just think it's a really brilliant way to start. So the point is, if root 2 were a rational number, I could write it as N over M. Yeah? So hold on. We'll get to the proof in a second. So one of the things I need to sort of teach you, now this is why I asked for it, is how to do proofs. So right now, I mean, maybe you can't tell, but what kind of proof should I probably use to do?
Just a contradiction.
It's going to probably be a contradiction proof, because, also, if you don't know if I write some symbols you don't understand, please interrupt me and ask me what they are. I mean, this is not ENQ. Alright. But the reason this contradiction, because it's really shitty it's really bad to assume something's irrational because you can't say anything about it. Right? What does it mean to be irrational? It means you're not in Q, right? It's much easier to say what it means to be in Q. Does that make sense? So this is kind of how you can tell this should probably be a contradiction. So let's say I was going to write the proof for this. So I should start with something like this. Assume, for the sake of contradiction, that root 2 is in Q. So again, especially the first week, I'm going to be spending a little time doing many more details than necessary. But the reason I want to do this is, look, and I'm promising you this because the grader will love you if you do this. Writing something like this is so important in a contradiction proof. I have read papers where they do these gigantic 4-page, 5-page proofs of by contradiction, but they never say something that they're doing it by contradiction. So the entire time you're like, this is just all false. This just can't be true. Blah, 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 blah. And then at the end they say, oh, contradiction. The point is, if you put something like this, it tells a reader, namely the grader or me if it's a midterm, that there's going to be a contradiction. So even though what you're about to say is not true, that's okay. That's what you want. Does that make sense? This is probably the most important thing of contradiction. So now what I have to do is kind of come up with something that just doesn't work. So anyways, if 2 was a rational number, Well, I could write, then we could write, oh yeah, I didn't say this during the thing. The other thing I'm going to mention is, this is a proof course. Proofs aren't like long pages of calculations, though they often involve long pages of calculations. They're actually paragraphs. This is like as a grad student, especially when I was in classes and doing homework every week, I was writing some 30 pages a week of proofs, but they're sentences. You can use symbols like it's not in, there exists, for all these things, but they mean words. Words come into the sentence like grammatically. It'll help you when you're studying off your homework. It'll help the grader know what you're talking about. It really does help. Because if you just put a bunch of symbols and this is Rudin, even Rudin, who I think was being like held, like they probably did not have enough ink when Rudin was writing this, because he skipped so much stuff. Even Rudin knows we use sentences in this. Okay. So then we could write root 2 equals n over n, m elements of z. So I could write root 2 is n over m for two integers. And here's something I'm going to say. Now this is analysis. I'm assuming you guys have had some math. And this is one of the things that's hard about this class. I'm allowed to say stuff that I didn't necessarily learn in this class. Now be careful, because there's calculus. This is calculus, so technically you can't use calculus. But something I can use is maybe I could say these two are in lowest terms, or these two are relatively prime, as in they have no common factors. Does that make sense? Right? Like you can write we already know you can write every rational number and with relatively prime numerator and denominator, right? With n and m having no common factors. Right? But so again, part of the reason I wanted to do this is a good example. I'm going to use a bunch of stuff about prime factorization in a second. But the reason I wanted to bring this up is that that's perfectly valid. That's perfectly valid math. You're allowed to use it in this class. I mean, I'm not saying the thing is don't use L'Hopital before I prove it, because we're going to prove L'Hopital. Don't say you can take a derivative before we talk about derivatives. But because that's what this class is about. But stuff like prime factorization of stuff, that's fine. In fact, if you guys have taken 110 and something comes up and it's like a consequence of something in 110, I'd be okay with you using it. It's not going to affect you, because you should be able to do every problem without having to take it. That's my point. Is that feel free to use stuff from other classes as long as it doesn't step on the stuff we're going to cover. Alright? Because you don't want to do circular stuff. It becomes a problem. Fine. But so n over m have no common factors. Great. So but this tells me, now what that means that m times, so now this implies, oh yeah, that's the other thing. As the class gets going, I may start shortening my proofs a bit. For the bigger proofs, I'll lay out all the details. But this implies that m times root 2 equals n. Right? Squaring both sides. Both sides. Yeah. This, also, when you plan your lecture, you don't realize how long it takes to write words. So 2m squared equals n squared. Yeah? Great. So what does that tell us, guys?
That 2 is a denominator. Yeah, 2 is a factor.
Right. Or a nice way to say this is n squared is even, right? Because it's divisible by 2. But so that means, which implies, so I'll use this symbol just for fun. N squared is even. But if n squared is even, what else is even?
N squared.
I'll put giving. I know this is a run-on sentence, but I'm not perfect. But my point is, since you're doing your homework at home, you can that's the other thing, and it really does help in this class. Because my gosh, you'll see for the second part of the proof I'm going to do, some details you just need to do to address, because you need to work out the details, and then that's not the way you write it in. Giving n is even. So